My name is Caroline. I am PhD student at Aeronautic Institute of Technology. My paper is Optimizing Swing Foot Trajectory of Humanoid Robot Walking for Energy Efficiency. Let's start with the introduction. Humanoid robots are fascinating because they have a human-like appearance. However, their behavior is different from humans. Geometry accompanied such as servers restrict the kinematic chain of a humanoid. As a consequence, the movement comes with high energy expenditure. Takenaka showed the difference in energy expenditure between walking a humanoid and a human. Collins showed the reasons why humanoids spend so much energy. Wee and Lee proposed a two-off and heel strike movement. With this, humanoids overcome the kinematic restriction and exploring other terrains. Fata and Faccheri employed polynomial interpolation to optimize the position of the angle of the oscillation leg foot for less energy expenditure. We use covariance matrix adaptation evolution strategy because it used to study humanoid movement, especially in 3D humanoid robot soccer. Our problem formulation. We implement the CMAES to find parameters that define the oscillation foot trajectory, especially for our custom-made robot Chappie. Figure 1 shows real Chappie. We know of literature that 80% of the humanoid gait corresponds to the swing phase. In swing phase, only one foot is in contact with the ground. Therefore, we use simplified hypothesis for the model. We consider only the swing leg in sagittal plane. We consider the body fixed. We consider the simulation time corresponds to the swing phase time. We implement our walk algorithm following the steps below. With the parameters obtained by CMAES, we find the foot trajectory swing. By inverse kinematics, we find the joint angles, in our case, the hip, knee, and ankle joint. After that, it uses them as references for the position control. Therefore, the measured energy corresponds to the efforts to obtain the swing leg pitch angles. In figure 2, in A, the beginning of the swing phase, and in B, the end of the swing phase, where θ1, θ2, and θ3 are the pitch angles of each joint of swing leg, and θ2 and θ heel are the parameters obtained by CMAES. Mathematical model. For the dynamics of the swing leg, the kinematic chain considers three links. This equation can be derived using Lagrangian mechanical. Theta is the joint variable vector, m is the inertial matrix, c is the vector of Coriolis, g is the vector representing gravitational torques, tau is the vector of control input torques of three joints. For the cost function, we want to minimize the electrical energy dissipated by the servos, in our case mx28, where r, k, and eta are servos parameters, and tau is the vector of current and torques all joints. Our methodology is divided in two approaches. In the first approach, we fixed the step frequency. Therefore, we only have two optimized parameters given by CMAES, in the case θ2 and θ heel. In the second approach, We optimized step frequency. We have three optimized parameters, theta 2, theta hill, and frequency of the step. Due to the scale difference, we normalized with the minimum and the maximum values of the optimization parameter from 0 to 1. The results for fixed step frequency. The function converts to this value with parameters with the following value. Theta 2 is 25.87 degrees and theta hill is minus 24.03 degrees. In comparison, the swing foot without two-off and heel strike have a cost of this value. Therefore, we can infer a cost reduction of 53.53%. Figure 3 shows best cost function per interaction with two-off and heel strike. The results for optimized step frequency. We analyze three situations. With each situation, the walking robot has a different velocity. Figure 4 shows best cost function, but the cost is parameterized by step length. From this point of view, we know that speed of 0.3 is the most advantage. In Table 1, we show that the parameters result optimization for different speeds. It's important to mention this cost is in absolute value. Now, let's watch a video corresponds to the movie for the speed of 0.1. Conclusions. The CMAES proved to be very useful for our problem. Biologically, humans spend more energy when they walk faster. Our paper proves that for our robot, this influence of speed on energy expenditure has similar behavior to humans. We may apply the same methodology in other robots, needing to change the parameters used to model the kinematic chain and actuators. In the future, we will measure the energy used for the flow rates. We want to thank CAPES for financial support and our sponsors. These are the references we use in the presentation. Thank you.